Let's start with a pretty straightforward AP example. The graph of f shown above, off to the right, sorry, consists of 6 line segments. Let g be the function given by g of x equals the integral from 0 to x of f of t dt. So here, I am given an accumulation function g of x, which depends on the function f of x, and that is the graph that I've been given, the graph of f of x. And notice that we have been given a description of g where it's a bunch of different line segments, which we can see, but they're always going to describe that for us. So in part A, we're asked to find 3 different quantities, g of 4, g prime of 4, and g double prime of 4. So let's go ahead and get started. Let's find g of 4 first. So this is g of x right here. G of 4 simply means if I substitute a 4 into this x, a 4 needs to go into this x here in the upper limit of integration. So g of 4 equals the integral from 0 to 4 of f of t dt. So now, this is not a numerical quantity yet, but I can find this value by looking at the area under the curve f of x between 0 and 4. So here's the x value 0, here's the x value 4. I need to find the area of this triangle that's below the x-axis, kind of missed a little bit, and then I need to find all of this area here of this trapezoid. But notice I have some symmetry going on here. This triangle, this piece, is going to be the exact same area as the one below the x-axis, so these two pieces are going to cancel out. So the integral from 0 to 4 is really just going to be the area between 2 and 4 in this case. So I'm going to go ahead and find the area of this rectangle and the area of this triangle separately. So I'm just going to say the area of the rectangle is, of course, 1, the base is 1, and then the height here is 2, right? So don't be fooled by like the values that are right here. Notice that the height of this is 2, so try to just think about, this base being 1 and this height here being 2. And of course, I am not going to simplify. This is AP free response, so I'm just going to leave it as 1 times 2. And then plus 1/2. And then the base of this triangle is 1 as well. And the height is, of course, 2 again. And again, no need to simplify. Now I have numerical answers. And that's it. I am done with g of 4. So now I need to find g prime of 4. So it's important we find g prime of x first. I always want to find generic derivatives first. So remember that the FTC part 2 in our case allows us to take the derivative of an integral with a variable or a function of x in the upper limit of integration by just substituting that right into the dummy variable t. So g prime of x is equal to f of x in this case, right? So if I take the derivative, I put a derivative in front of this integral, this x is just going to replace this t. So g prime equals f of x. And once I know this piece of information, what I should do is go over to the graph and relabel it f equals g prime. So I remember that this graph is g prime of x as well. So now I want g prime of 4, which is equivalent to finding f of 4. So this is the graph of f, this is the graph of g prime. So if I want g prime of 4 or f of 4, I'm really just looking for the output value. So this coordinate point here is 4, 0. So the output value is 0. So g prime of 4 is 0. Just I'm looking at the y coordinate in this case. But when I need to find g double prime of 4, then the next connection I need to make is that if I take the derivative of g prime, I get g double prime, which is going to be f prime of x. So g double prime of x is equal to f prime of x. So g double prime of 4 is equal to f prime of 4. And if this is the graph of f, and I want f prime of 4, I'm looking for the slope of this particular line. One of the things I want to point out is when I'm in search of a slope, I never estimate. I never, ever, ever estimate. So I will often be given at least two exact coordinate points, specific coordinate points on that line. And one of them may not be the particular x value that you're trying to approximate the derivative at. So in other words, if I didn't know that this coordinate point was exactly 4, 0, I could use two other points on this linear piece, on this line segment. So I'm actually going to do that for this example just to make my point, is that to find f prime of 4, I need the slope, and I have 2 points on the line. So I could use the point 4, 0, but I could also use these 2 points here that I've been given. So the slope is y2 minus y1. So I have 2 minus negative 2. So I'm choosing to call this, my y1s and my y2. So 2 minus negative 2, and then over 3 minus 5. I subtract my x values, I subtract my y values, and we just make sure to keep them in the right order. So 2 minus negative 2, 3 minus 5, and that's it. So remember, we don't need to simplify. So on free response, we just leave our answers once they are numerical values. So I could not have left my answer as f prime of 4 or f of 4. I needed to get to these quantities here. All right, part B. Does G have a relative? And let's remember that relative means local. Does G have a relative or local minimum, a relative or local maximum, or neither at the x value 1? Justify your answer. So remember that a function, the name of the function is g. The function g is going to have a local min, local max, or neither, depending on whether or not we have a change in g prime from positive to negative or negative to positive. This is the first derivative test. So for part B, let's go ahead and look at the x value 1. So right here at 1, remember this is the graph of g prime. Well, as I look from left to right, g prime is changing from below the x-axis, where g prime is negative, to above the x-axis, where g prime is positive. So what we want to say is that at x equals 1, g prime changes from negative to positive. So G has a relative minimum. So any change from negative to positive on the derivative means that G is changing from decreasing to increasing, and remember, decreasing to increasing is a relative minimum. And that's it. Our justification is there. And we can move on to part C. Part C is saying, suppose f is defined for all real numbers x and is periodic with a period of length 5. So that means we have to remember some stuff about honors math analysis a little bit. For a function to be periodic with a period length of 5 means that this function is going to have the same pattern basically every 5 units. And we can kind of see that here between negative 5 and 0. I have these 3 pieces of the line segment, and then I have the same 3 pieces of the line segment. So what we're saying is that, it's going to keep going like this. That's what it means to be periodic. The graph above shows 2 periods of f. Given that g of 5 equals 2, find g of 10. And then write an equation for the line tangent to the graph of g at x equals 108. So this is really going to take some thinking about here. So we know that the value of g of 5 equals 2, and the first thing we're being asked to find is the value of g of 10. So I want you to keep in mind that this is the graph of g prime, and we need to find the value of g of 10. And when I do what I'm about to do, you're going to think, where did that come from? And I completely agree, it's not an intuitive thing to do, and that's why I'm showing it to you so that you remember to do it. So again, I have g of 5 equals 2, I want g of 10, and I have the graph of g prime. So I'm actually going to use the FTC part 1. And I'm going to cleverly choose my limits of integration to be 5 and 10. And you'll see why in just a second. So what I'm going to do is I'm going to integrate 5 to 10 of the function g prime of x. So I can find this particular value. This is a number. The integral from 5 to 10 of g prime of x. So here's the graph of g prime of x. So 5 to 10 is one period of my graph, and in fact it's going to be the exact same area as the one from 0 to 5 because it's the same period. So if I find let me try to use a different color here. So if I find the area all the way from 0 to 5, that's the same as finding, so all these pieces here, that's the same as finding the area from 5 to 10. And look at all this symmetry. We already said this piece and this piece cancels, this piece and this piece cancels. So really, this integral from 5 to 10 of g prime of x, because remember, this is g prime, is just going to be the area of this little rectangle right here, which has a base of 1 and a height of 2. So we can in fact tell that this particular area is 2. Now, why is that important? It's important because we should recognize the FTC part 1 right here. The FTC part 1 says, find the antiderivative of g prime. So the antiderivative of g prime is g. And then we plug in the top and bottom limit of integration and subtract. So the integral from 5 to 10 of g prime of x is g of 10 minus g of 5. So why is this important? Well, we're trying to find g of 10. And we know g of 5 is 2. So this area was 2. And this area has to equal, by the FTC part 1, g of 10 minus g of 5. And g of 5 is 2 because that was given. So if I add the 2 to the other side, then I know my value for g of 10 is 2. So that's tricky. I definitely agree that that's tricky, but this trick here of, where did this integral come from? It just came out of nowhere. Yes, it absolutely did, but it's a trick that we're going to use over and over again applying the FTC part 1. So now we've answered the first part, find g of 10. Now the last part, write an equation for the line tangent to the graph of g at x equals 108. So tangent lines definitely don't go away. They're going to keep coming up a lot for the rest of the semester as well. So let's remember how to find tangent lines. We need a point and a slope, right? To find the equation of a line, we need a point and a slope. We need a point on the graph of g. So the x value is 108, so our point is going to be 108, comma g of 108. So we're going to need to find g of 108, and our slope is g prime of 108. So let's try to remember something, the whole idea of this graph being periodic. So I'm not going to draw, a whole bunch of copies of this graph. What I'm going to do is recognize that since it's periodic every 5 units, that would mean that 0 is kind of like 105, and this is 106, and this is like 107, and this is like 108, and this is 109, and this is 110. So this same looking graph is going to occur between 105 and 110. Alright, so I need g prime of 108. So remember, this is the graph of g prime of x. And way over at 108, way down there, it's going to look the same as this, integral, or this interval from 0 to 5. So g prime of 108, that's just the y value. So g prime of 108 is 2. So that's my slope, right? That's my m, because I'm going to plug this into my y minus y1 equals m. So there's my m, x minus x1. Well, I actually already have x1. That's 108. So I can plug that in. Got a little cramped there. But now I need to find g of 108. Well, once again, we had the value of g of 5. We want the value of g of 108, so we can do that same little trick where I go from 5 to 108 this time of g prime of x and dx, and then that's got to equal g of 108 minus g of 5. So I will be able to find g of 108 because g of 5 is 2. This is going to be a little trickier. The integral from 5 to 108 of g prime of x. Alright, so remember that every 5 units, a bunch of stuff was going to cancel. Right, so all this piece, all this piece, all this piece, and all this piece. So every 5 units, I'm really only going to tack on 2 each and every time. So the integral from 5 to 105. So between 5 and 105, I'm crossing 100 units. But every 5 units, I'm adding up 2. So 5 to 105, let's kind of try to break this up. So 5 to 105 of g prime of x plus 105 to 108 of g prime of x. I can find that area. So 5 to 105, that's 20 copies of 5. And each copy of 5 only added 2 units on. So this is going to be 2 times 20. So again, every 5 units, I'm tacking on 2 units to this sum, right? Because I'm adding up a bunch of sums. So between 5 and 105, there's 20 copies of 5, and every copy of 5, I'm adding on 2. So that's why I'm multiplying 2 times 20. It's definitely a pattern recognizing situation. And then I have to add on the area from 105 to 108. So 105 to 108, remember this first period of 5 acts like 105 to 110, so if I'm trying to go from 105 to 108, that's just an extra copy of 2. So 2 times 20 plus 2 is equal to 42. So 42 has to equal g of 108 minus 2. So g of 108 minus 2, sorry I'm running out of space, equals 42. So let's kind of bring this over here for a second. 42 equals g of 108 minus 2. So if I add 2, 44 equals g of 108. So that's the y value of my point. So y minus 44 equals 2 times x minus 108. That was obviously a very tricky question. That requires you to know a little bit from the past, the idea of periodic, and again, this concept that came up twice in one problem, that we just had to make up our own definite integral where I can use the Fundamental Theorem of Calculus Part 1 to find a particular value. All right, let's go ahead and take a look at this AP problem. We're told the continuous function f is defined on the closed interval here from -4 to 3. The graph of f consists of 2 quarter circles and 1 line segment as shown in the figure above. I moved the figure to the right, so it's not above, it's off to the right. So this is the graph of f, and we're defined on the closed interval from -4, that's the x value over here, so we can add a little more detail to our graph if we want to. All the way up to the x value 3. And notice that they're just going to always describe for you what's happening in particular on this graph. So this is a quarter circle. You don't have to guess. We are told that it's a quarter circle. And this piece down here is a quarter circle as well. And then, of course, this is a line. So that's described for us. And then we're told let g of x equal 2x plus the integral from 0 to x of f of t dt. So since we have an accumulation function, right, we have an x in the upper limit of integration, we should already be thinking the FTC part 2. So let's go ahead and take a look at the problem. In part A, we're told to find g of -3. So let's go ahead and answer that part of the question first. This function is g of x. So if I want g of -3, that means wherever there is an x in this function, I'm going to replace it with the value 3 and solve. So for part A, we're trying to find g of -3. So we're going to have 2 times -3 plus the integral from 0 to -3 of f of t dt. All right. So this portion here is not a numerical value yet. So we are going to have to find this particular value for this definite integral using the graph of f. So really here we're trying to find all the area from 0 to -3. So because the lower limit of integration is bigger than the upper limit of integration, the first thing we'll go ahead and do is switch the limits of integration, which would make this plus a minus. So notice that I'm going to leave 2 times -3. I'm not even going to simplify that because there's no need to. And when I switch these limits of integration, I'm going to get from -3 to 0, so -3 is the smaller value, of f of t dt. And now my job is to evaluate this integral, the integral from -3 to 0 of f of t dt using the graph. So -3 to 0 on the x-axis means I'm looking for the area of this quarter circle here. So this portion right here is going to become 1/4 pi times my radius squared. So the area of a circle is pi r squared, but we have a quarter circle, so we need 1/4 of that. And the radius is going to be 3 units. So the radius of this circle right here, so notice this is a total of 3 units. So 1/4 pi times 3 squared, and that is being subtracted from 2 times -3. And I'm going to leave my answer like this. This is a numerical answer. So I'm just going to go ahead and box this in. That is my answer for find g of -3. But we're also asked to find g prime of x and evaluate g prime of -3. So find g prime of x, that means find the derivative of this function here. So since these two pieces are being added together, I can find their derivatives independently. So g prime of x is equal to 2, because I'm taking the derivative of 2x, that's just 2. And now, the derivative of this area function, this accumulation function, well, the derivative in front of this integral right here, where a variable is in the upper limit of integration, is just going to turn into f of x, because that x is going to be replaced by the t here. So the derivative is 2 plus f of x. So that is the answer for find g prime of x. And then evaluate g prime of -3. So now, once we find the derivative, it's always important to write out the derivative function. Now we can evaluate the derivative function by plugging a -3 in. So we have 2 plus f of -3. And I want to point out we cannot leave our answer like this. F of -3 is not a number yet. So we have to find the value f of -3. Well, this is the graph of f. So if I want f of -3, I'm literally looking for the output value, the y value. So I'm going to go to the x value -3. So this coordinate point here is -3, 0. So the output, f of -3, is 0. So I have 2 plus 0 is my answer for g of -3. So here are my 3 answers for part A. Moving on to part B, and part B is a bit rough. We're asked to determine the x-coordinate of the point at which g has an absolute maximum on the interval from -4 to 3, and this is a closed interval. And we need to justify our answer, and that means that we really need to show all the work involved. So if I'm interested in finding an absolute maximum on the function g, I need to test the endpoints of the closed interval as well as the critical points into the original function g. So I have my endpoints. I'm going to need to figure out, well, what is g of 3? I need to figure out what is g of -4. And then I need to also evaluate what is g of the critical points. Alright, so to find critical points, I need to know where the derivative of g, where g prime equals 0. And this is a tricky question because on this particular problem, g prime of x is not exactly equal to f of x. So I want you to notice I did not label this graph g prime of x because g prime of x is f of x plus 2. So if I want to find the critical points of g, I need to set g prime of x, which equals 2 plus f of x, equal to 0. So I'm going to do that over here. I need g prime of x to equal 0, which is f of x plus 2 equal to 0. And I have the graph of f of x here. So what I'm going to do is think about this as, where does f of x equal -2? So I want to know at what x value does the y value -2 come out on this graph. So here's the y value -2. So that occurs right here, which is at the x value 2.5. And we're not guesstimating looking at the graph. We can find that this value is 2.5 exactly because we have two specific points on this line. We have this point up here at 0, 3 and this point down here at 3, -3. So we can find the slope of this line exactly to verify that this is 2.5. So it in fact is the x value that we are in search of. X equals 2.5, or 5 over 2, is my critical point. So I also need to evaluate what's happening at 2.5 in the function g. So remember, absolute maximum is what's the biggest y value. Now ultimately our answer will be an x coordinate, will be either 3, -4, or 2.5, but to find which of those three x values the answer is, I need to compare the y values to find where the absolute maximum occurs. So we are substituting in these three x values into the function g of x, right? G of x is up here. So what I need to do is evaluate g of 3. So remember, that's 2 times 3 plus the integral from 0 to 3 of f of t dt. So I actually want this output value. And since I have to compare which one's bigger, which one's smallest, I'm actually going to simplify this. So 2 times 3 is 6, plus now I need the integral from 0 to 3. So if I look at this from 0 to 3, there's some symmetry going on. I have this triangle, that's the area from 0 to 1.5, and then I also have this triangle down here, and that's my area from 1.5 to 3. So notice that symmetry where the same area is above as is below, so this is going to cancel out. So I really just have 6 plus 0. So the output here is 6. Alright, so now we have to look at what is g of -4. So 2 times -4 plus the integral from 0 to -4 of f of t dt. Just like part A, I'm going to have to flip the limits of integration here. So I'm going to have -8 minus the integral from -4 to 0 of f of t dt. So what I have is -8 minus, and I'm going to put a big set of parentheses here because I'm now going to find the integral from -4 to 0. So that is this portion here, which is negative because it's below the x-axis, and it's a quarter circle. So we're going to have -1/4 and then times pi r squared. So I'll just put the pi back here for now. So the radius of this quarter circle, there's only one unit here as my radius. And then plus the area of this quarter circle up here, but we already found that value in part A. So I'm just going to go ahead and, well, this portion here, part of it is in part A. So it was 1/4 pi times 3 squared. So we're going to add 1/4 and then pi times 3 squared, right? I didn't want to include this 2 times -3 portion because I'm just interested in now finding the area of this quarter circle and the area of this quarter circle. Alright, and now we want to simplify as much as we can. So we have -8 and then we have minus. So inside here, let's see, what do we have? We have -pi/4 and then plus, so 3 squared is 9. So we have 9 pi/4. So now inside here I have 8 pi/4, which is 2 pi, and I'm subtracting that. So this is -8 minus +2 pi. So this is as simplified as I can get it. I never ever want to substitute an approximation in for pi. So I want to know what that approximation is, that it's 3.14, but I don't ever want to plug in 3.14 in for pi ever. So I'm just going to leave my output like this for now. And then I need to know what's going on at g of 2.5. So we have 2. I'm going to rewrite 2.5 as 5 over 2. And then plus the integral from 0 to 2.5 of f of t dt. So let me go ahead and try to draw a little line to segment our work. Alright, so hopefully you can see why I wrote 2.5 as 5 over 2, because these are going to cancel. So I have 5 plus the integral from 0 to 2.5 of f of t dt. So 2.5, see if I can go ahead and erase this little piece and try a different color. So to 2.5 means I'm going to stop right here. So I need all this area, which would be negative because it's below the x-axis, and all this area here, which is positive because it's above the x-axis. So 5 plus 1/2 Now my base right here is 1.5. I'm going to choose to write that as 3 over 2. And then times my height, so the height of this triangle is 3. And then I'm going to need to subtract the area of this triangle here, so we have 1/2, and the base here is going to go, this is from 1.5 to 2.5, so my base here is 1, and then my height, well, remember that our output here was -2. I'm sorry, 2, because we don't want, it is below, but we're thinking about it as just the area, as in this distance here, or this height is 2. We don't want to think about it as negative. Right here, we already took into account the negative because it's below the x-axis. So we finally have 5 plus, here if we multiply all this out, we're going to get 9 over 2, and then we're going to get minus, well, this 2 and this 1/2 will cancel, so we're just going to get -1. So now let's go ahead and simplify even further. So what we have here is we have 5 plus, so let's think about this as 4.5 minus 1. So we have 5 plus 4.5, that's 9.5, minus 1 is 8.5. So what we're doing is comparing all the outputs. We have 6, we have -8 minus 2 pi, we have 8.5. So if we compare these, 8.5 is the biggest, right? So -8 minus 2 pi, that's negative. So that's not the absolute maximum. And then, of course, between 6 and 8.5, 8.5 is bigger. So here's where we have to be careful with what the question is asking. The question is asking, determine the x-coordinate of the point at which g has an absolute max. So the x-coordinate, where that happened, is at 2.5. So what we would need to say is, at x equals 2.5, or 5 over 2, g has an absolute maximum. So 2.5 is not the absolute maximum. At x equals 2.5, g has an absolute maximum. So it's a very important difference in the way that we word things. So 8.5 is the absolute maximum, but at the x value 2.5, g has an absolute max. So that's our summary, that's our conclusion. We would need to write that down. And all this work, this is our justification. So we want to be clear that explain means we need to have, a sentence or a fragment, but justify means you can't just put x equals 2.5 and that's it. Justify means show your work, and checking the endpoints, checking the critical point is our justification. Part C. We want to find all values of x on the interval from -4 to 3. It's an open interval for which the graph of g has a point of inflection. Give a reason for your answer. So we have to remember how to find inflection points given a function. So given g, we need to know where g double prime equals 0 or is undefined, and g double prime has to change sign. So remember, if the second derivative equals 0 or is undefined, that's a possible inflection point. So we're going to need to know where the second derivative of g equals 0 is undefined and changes sign. But right now, we have f. So we need to make the connection between g double prime and f. So for part C, let's start out by figuring out the relationship between g double prime and f of x. So we had written down that g prime of x equals 2 plus f of x. So if I want the second derivative, if I want g double prime of x, that's going to equal, well, the derivative of 2 is 0, and the derivative of f of x is f prime of x. So what I need to know is, where does the second derivative equal 0, or where is the second derivative undefined, and where does the second derivative change sign? But g double prime is equal to f prime of x. So we want to know, when does f prime of x equal 0, or where is f prime of x undefined? So this is the graph of f. Let's make that bigger. This is f of x. So we want to know, where is the derivative of this graph 0 or undefined. So we are looking for either horizontal tangent lines on this graph or corners or cusps. or vertical tangents, because those are going to be places where my first derivative, f prime of x, is 0 or undefined. And remember, this is an open interval, so we're not considering the endpoints. So if I look at this graph of f, and I'm looking for, again, horizontal tangent lines. Well, some people might say that happens right here, but remember, we're not considering endpoints. So as I move along, right here I can see I have a sharp turn. So at the x value 0, I have a place where f prime of x is undefined. So that means x equals 0 is a possible inflection point. And also any vertical tangents. So we can see that that happens right here at -3. So at 0 and at -3, those are places where f prime of x is undefined. There are no horizontal tangent line locations on the open interval from -4 over here to +3. But there are two places where I have possible inflection points. So I'm going to call them possible inflection points for now. We also need to see whether or not the sign of g double prime changes, or the sign of f prime. This is going to take some thinking about. The sign of f prime is slopes. Is the sign of the slopes changing? So as I move over here from left to right, these slopes over here are all going to be positive. So what I'm going to do is I'm going to put a bunch of little pluses right here. All of these slopes of tangent lines are positive, right? If I draw little tangent lines, that's what I'm doing now. All of these slopes are positive. So at -3, where I had a vertical tangent line, that is a place where f prime is undefined because it's a vertical tangent line. But the sign of f prime did not change because the slopes were positive over here, right? Little tangent lines. The slopes were positive and then the slopes stayed positive. So -3 is not an actual inflection point. But notice as I move along, positive slope, and then boom, right after 0, this line, this linear segment here, has negative slope, right? The same negative slope everywhere. So 0 is the only value that is an actual inflection point. So this is not, my conclusion is that x equals 0 is an inflection point because g double prime, which equals f prime, is undefined at x equals 0, and g double prime, which equals f prime, changes sign. This is a tricky one. This really takes a lot of thinking about because everybody just wants to look at where the function crosses the x-axis, and that had nothing to do with it. -3 was not a possible inflection point because that was a 0 of f. It had everything to do with the fact that there's a vertical tangent line there. And at vertical tangent lines, the derivative is undefined. That's what we were looking for. And at sharp corners, the derivative was undefined. So this was a very tricky part C. Part D. Find the average rate of change of f on the closed interval from -4 to 3. So we're going to stop right there and solve that first part. So the formula for average rate of change of f on an interval from -4 to 3 is, so average rate of change, we're thinking the difference quotient, right? Not the limit of a difference quotient. That would be instantaneous rate of change. That would be the derivative. So we're going to do f of b minus f of a. So f of 3 minus f of -4 over 3 minus -4. And this is the graph of f. So f of 3 is -3, right? Because we're just reading the graph for exactly what it is. We're looking at the y values. So we have -3 minus f of -4. So f of -4 is the y value -1 over 3 minus -4. So far, no simplifying is required. We will have to in a minute, but for now, that is the answer to the average rate of change. Now, the rest of the question says, there is no point C between -4 and 3 for which f prime of C is equal to that average rate of change. So what this is saying is that there's no place where f prime of c equals this numerical value. Explain why this statement does not contradict the mean value theorem. So remember, the mean value theorem said, well, if f of x is differentiable and continuous, then there has to be a place c such that f prime of c equals f of b minus f of a over b minus a. So this is the conclusion of the mean value theorem. But the hypothesis of the mean value theorem says that we need our function f to be differentiable and continuous in order for this conclusion to occur. So explain why this statement does not contradict the mean value theorem. Well, the reason why this statement does not contradict the mean value theorem, why there is no such point that this occurs, is because the function that we can see here has a problem with this hypothesis. So this function that we're looking at has no problem with continuity. I can draw this graph without lifting my pencil. But there are two places where this function fails to be differentiable on the interval from -4 to 3. At -3 and at 0. So there's a vertical tangent line occurring right here at -3, and there's a corner or a cusp at 0. So explain why this statement does not contradict the mean value theorem. So we would have to write, this statement does not contradict the MVT because f of x fails to be differentiable at x equals -3 and x equals 0. But really just finding one place of non-differentiability would be fine. So this statement does not contradict the MVT because f of x fails to be differentiable at x equals -3 and x equals 0. So the conclusion must not be true. So this was just, this part we would not have to write down. Just to clarify, I was just going back to explain it, that the hypothesis says that if f is differentiable and continuous, then this must occur. There must be some c such that the derivative at c equals f of b minus f of a over b minus a. So what we found, just to explain what's happening, what we found in the first part, find the average rate of change, we found the slope of a secant line. So between this point here and this point here, go ahead and try it in a different color. So between this point here and this point here, there's 2 points, so I'm finding the slope of the line between those 2 points. And if this function was differentiable and continuous, there would have to be some other place that had a tangent line with the same slope. But we can see, we said earlier, all these slopes over here were positive. This is clearly a negative slope. And then the slope of this line here is clearly not the slope of this line. So there isn't some c value where the slope of the tangent line somewhere is the same as the slope of the secant line. That doesn't happen. And the reason why it doesn't have to happen is because the function fails to be differentiable at least one value, in this case 2. Alright, let's go through this one. The figure above, to the right, shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval from 0 to 8. F prime, the graph of f prime, has horizontal tangent lines at 1, 3, and 5. So we can see that on the graph, but we've been told it in words. And the area of the regions between the graph of f prime and the x-axis are labeled in the figure. So we're told exactly what these little regions, area is exactly without computing it. The function f is defined for all real numbers. So remember, we have not been given the graph of f. We've been given the graph of f prime. But f is defined for all real numbers, and here's one value on the graph of f. F of 8 equals 4. And let's keep in mind, we're never given information in these free response that we won't need at some point. So part A, find all x values on the open interval from 0 to 8, for which the function f has a local minimum. Justify your answer. So this is a review problem. If this is the graph of f prime, local minimums of f occur where f prime changes from negative to positive. So on the graph of f prime, f prime is changing from negative below the x-axis to positive above the x-axis right at this value here. So we're just going to have to be careful and count 2, 3, 4, 5, 6. So at the x value 6. So what we would say is x equals 6 because f prime changes from negative to positive. So below the x-axis to above the x-axis. So there's our answer. There's our justification. Part B. This one's going to be longer. Determine the absolute minimum of f on the closed interval from 0 to 8. Justify your answer. So when we try to find absolute min and max, we need to test the critical points and the end points into the original function f. Again, we've been given f prime. So we need to check the endpoints in f. So we need f of 0, we need f of 8, and we need to check the critical points of f of x. So I'm going to need to check the critical points. There are 3 critical points. So remember, critical points, let's write this down, would be where f prime of x equals 0. So f prime of x equals 0 at 3 places. At x equals 1, at x equals 4, and at x equals 6. Now I'm going to try to save you some work. Only one of these 3 critical points has the potential to be an absolute minimum value. Let's remember that if the sign of f prime does not change, there is not a local min or a local max at that value. So at 1, that's neither a local min nor a local max. So neither local min or a local max. We already said 6 was the x value of a local min. And 4, f prime changes from positive to negative at 4, so this is going to be a local max. So I only have to check the x value 6, the critical point 6, because there's no way a local maximum is going to be an absolute minimum. The absolute minimum is the smallest possible y value. If at x equals 4 there's a local max, that can be the smallest possible y value. And 1 is neither a local min or a local max. So I can eliminate those as values, as critical points that I even have to bother with. So I only have to figure out what is f of 6. Alright, so now one of these 3 values has been given to us. So yay us, right? There's that piece of information that I was given that I was going to need. So f of 8 equals 4. I already know that. So now I need to find f of 0 and I need to find f of 6. And here's where we're going to use that FTC part 1 trick. So I have the graph of f prime of x. I have the value f of 8 and I need the value f of 4. So over here off to the side, what I'm going to do is I'm going to set up an integral where one of the limits of integration is 0 and the other limit of integration is 8. And the integral integrand is going to be f prime of x. Alright, so 0 had to go on the bottom because that's the smaller number. 8 on the top, that's the bigger number. But why did I choose 0 and 8? Because I'm in search of f of 0 and I have f of 8. And by the FTC part 1, the antiderivative of f prime is f, so this quantity equals f of 8 minus f of 0. Now, I can find this area, the area under the curve f prime of x from 0 to 8, and I can in fact find this pretty quickly. So here's 7 and here's 8. The reason I can find it quickly is because this nice graph tells us the area of each region all the way from 0 to 8. So remember, all the area above the x-axis is positive. So 2 plus 6 plus 7 is being added together. So the area on top is 15 minus the area below. So minus 3 is 12. So this whole quantity here is 12. So it's because I'm integrating, finding the area under f prime. Here is the graph of f prime, all the way from 0 to 8. So I want a numerical value for this. Because I have a numerical value for f of 8, that's 4, which will allow me to find f of 0. If I just subtract 4, so subtracting 4 from 12, I get 8. So negative f of 0 equals 8. Divide by the negative 1. So negative 8 is equal to f of 0. So f of 0 is negative 8. And now I'm going to use that same trick to find f of 6. So I'm going to set up the integral from, so remember I was given f of 8 equals 4, so I'm going to keep using 8, and now I'm going to use 6 as another limit of integration. Well, 6 is less than 8, so I want 6 on the bottom, 8 on the top, and then f prime of x dx as the integrand, so that we can apply FTC part 1. This is f of 8 minus f of 6. Alright, so now I want the integral from from 6 to 8 of f prime of x. So this is f prime of x. From 6 to 8, the area is 7. We got it right there. No work needed. We were told that quantity. F of 8, again, was given. That is 4 minus f of 6. So if I subtract the 4, I get 3. So negative f of 6 is 3. So negative 3 equals f of 6. And there we go. Now we have to make our conclusion. What is the absolute minimum? So the absolute smallest output that comes out is negative 8. So here's our absolute min. And our justification is our work. So we showed that we knew that we had to check the endpoints. We knew that we had to check the critical points. But checking just 6 is perfectly fine and recommended because it's understanding that the other critical points, 1 and 4, had no chance of being the absolute minimum value because 1 was neither a local min or a local max, and if 4 was a local max, or at 4 there's a local max, there's no way it could be an absolute minimum. So this is my solution. Last two parts. Part C, on what open intervals contained between 0 and 8 is the graph of f both concave down and increasing? So remember, this is the graph of f prime of x. So in order to find where f is concave down, we need to know where f prime is decreasing. But if we also want f to be increasing, we need to know where f prime is positive. So this statement, where is the graph of f both concave down and increasing? It's like asking where is f both, or where is f prime decreasing and where is f prime positive? So f prime is positive where above the x-axis here. But we also need to know, more than that, where above the x-axis is this graph f prime decreasing, falling. So that's going to happen from 0 to 1. So f prime is decreasing, but above the x-axis. And then over here from 3 to 4. And that's it. So for part C, the answer is 0 to 1 and 3 to 4. And my reasoning is because what I just wrote up here to find the answer, because f prime is decreasing and f prime is positive on these intervals. So that was definitely a review question. But I think the biggest mistake here is that people would put where is f prime concave down, so they would write the intervals where that happens, and then separately they'd write down where f prime is greater than 0. So this question is asking for the intervals where both of these conditions are satisfied. And finally, part D. We're told the function g, so far we've not been told anything about g. The function g is defined to be the function f of x as a quantity cubed. If f of 3 is negative 5 over 2, find the slope of the line tangent to the graph of g at x equals 3. Find the slope of the line tangent to the graph of g at x equals 3. What I'm being asked to find in words is g prime of 3. I'm being asked to find the slope of a tangent line. That's a derivative. So find the derivative to the graph of g at x equals 3. Well, g of x is the composition f of x quantity cubed. So remember that we always find the generic derivative first. So g prime of x, right? We do not plug in 3 first. We find the generic derivative. So g prime of x, this requires a chain rule. So I have f of x is inside of x cubed. So the outside function's derivative is 3, we leave the inside the same, times f of x squared, because we reduced the power by 1, times the derivative of the inside. The derivative of f is f prime of x. Now we try to find g prime of 3 by substituting in a 3 for every x. So 3 times f of 3 squared times f prime of 3. So now we need a numerical value for this. So that's 3 and then f of 3. So f of 3 was given to us as negative 5 over 2. So negative 5 over 2 gets replaced by f of 3, and we had to square that quantity, times f prime of 3. So this is the graph of f prime of x, right? This is f prime of x. So if I want f prime of 3, I need to find 3 on the graph and just read the output value, which is 4. And since this is free response, we do not have to simplify. So this is our answer for g prime of 3. And that's what we were being asked to find in words. Find the slope of the tangent line, not an equation of the tangent line, just the slope of the tangent line. So that is the derivative.